There are 2 billion people in the world that don't have access to regular supplies of energy. If we're going to give them the same quality of living that we enjoy in North America and Europe, they're going to need energy, and we need answers for that. If the future of fusion was here today, it would change the way our energy system works dramatically.
We've only had the Fire Department of New York come once, where we generated enough smoke to trip off the smoke detectors in the building and have the fire department actually arrive and sort of shoo us out while they ventilated the laboratory. I've been involved in fusion research since graduate school 43 years ago. Columbia University, we work on magnetic fusion, and we're part of the US DOE-funded national program in producing magnetically confined fusion energy. Fusion is the ultimate energy source in the universe. All the stars in the sky, the sun, all of those lighted objects are powered by fusion. The process is really simple. You just take two light isotopes, hydrogen usually, bring them together, they react with a nuclear reaction, and they produce 100 times more energy than it takes in order to produce the reaction in the first place. The research on fusion that we're doing today is leading to a future where we could replace coal-fired, oil-fired, gas-fired power plants that we use today with fusion power plants. Publicly funded fusion research and privately funded, which is using investor money, want to develop fusion. We have got to constantly look for ways to make this project move faster.
Access 13. Right now we're at the Z facility. We're in the high bay that contains the Z accelerator. Z is the largest pulse power accelerator on the planet. It's noisy, it smells like oil. This is not a clean room. This is really how to make stuff happen. So if you were standing here during the shot, it would be your last few moments on Earth. The government is funding most of this work because it's very expensive and requires very big facilities. The Z machine, or the Z accelerator, first began life in 1985 as the Particle Beam Fusion Accelerator 2. In about 1996 or 97, there was an opportunity to change the configuration into a Z-pinch driver. The Z machine uses the magnetically driven approach. We have an energy storage section which consists of 36 large capacitor banks, and we're charging those capacitor banks up over about 3 minutes. We charge up the banks to about 20 megajoules of stored energy. Then we discharge all 36 of those Marks banks simultaneously. So we drive these targets from small spatial scales of order my thumbnail or smaller, and we compress them with large currents. And we also impose an externally applied magnetic field that we want to compress. So we're exploring what's called the magnetized target fusion approach.
We store between 22 and 26 megajoules of energy, which is anywhere between 26 and 52 sticks of dynamite. We hear it and we feel it.
When the machine fires, there's a lot of sound and the ground will roll. I just want you to stand with your feet about 2 feet apart, pointing at the center of the machine so you can feel the roll most effectively.
We've had coat racks fall over in the second floor of a building that's probably about 100 yards away. We've had picture frames fall. There's only one Z machine in the world. Everything else is pretty small compared to Z.
This is what would happen on the machine just after the shot that we witnessed earlier today. And some of that energy appears as high voltages that then flash over on the surface of the water as they find their way back to ground. Fusion in the 50s and 60s and 70s was oversold in that it is much harder than people imagined it to be first. You're trying to study plasmas which only exist for a few nanoseconds. There are a lot of ways that that process can go wrong. And you have to figure out, okay, in that last nanosecond, what's going on? Is it the way we thought it was going to happen, or is something really not quite what we expected? So it's discovery science at the limit of what's possible to do in the laboratory. Our goal, and for much of the world that is studying fusion, is still physics feasibility. And we may be 30 years or 40 years away from a practical fusion energy technology. So you obviously have to really believe in something to dedicate your whole life to it.
The scientific standards that are necessary to get public funding are quite high. The projects that you try to do tend to be the lower risk, longer time scale. Usually the private sector tries faster ways to do fusion. Those companies try to find an approach to fusion that they think is quicker, smaller, will cost less.
Fusion energy has the potential to provide this to the world.
But there's no free lunch in research. It means it's riskier.
General Fusion's had a little north of $100 million invested to date in private capital. Fusion has been pursued a lot by governments for many decades because of the promise of the technology. What is new has been the advent of private companies. The science and R&D that's gone on in the public sector, combined with the pace of innovation we're seeing elsewhere in the economy, when you get new news about fusion, it naturally attracts that attention. So the machine behind me here is a prototype of the compression system that we want to build. So we form plasma and we compress. Now this is a smaller scale than what a power plant would be, so there's no putting plasma into this. This is the compression system, and it's a central tank about 1 meter across that we can fill with molten metal, and then around it are these 14 big pistons, these big drivers that will compress and collapse a cavity that's formed inside that liquid metal. In the formation process, we're already going to be 4 or 5 million degrees C. And the compression is going to heat it another 10, 20 times to 100, 150 million degrees C. The best way to think about how hot that is to look up in the sky and look at the sun. This is really the heart of the Spectre machine. The plasma is formed from down below, and it bubbles up into this sphere here. And then all around what you see are diagnostics for measuring what's going on. So there's large laser systems, and then you see lots of optics here. And those lasers are used to measure things like the temperature of the plasma at different points, or the strength of the magnetic field, or the density of the plasma. It can be very challenging to work on fusion. It works great at the scale of the sun to create the conditions for fusion, but we can't do that here on Earth. We're not even close to being as big. We have to throw a lot of energy at this fuel to get it to 100 million degrees, and then we've got to hold it there long enough to react enough to produce more energy out than we put in.
We've had decade after decade of smaller companies try to find a faster, cheaper way to fusion. None have been successful so far. You presumably have uncovered some new approach, new wrinkle that makes you think that what you're going to do will succeed, whereas other people who tried this approach have failed.
The hardest thing to answer in this game is how soon. What we have a good line on is the next 4 or 5 years. We really want to take what we're doing here at General Fusion at the scale of big subsystems and prototypes like this one, and turn that into a large-scale integrated machine, produce conditions like what we need for fusion. So the idea that people have been up against certain problems forever and ever and ever, I don't think is actually true. We've, as a field, and a lot of this goes to really good hard work in the national labs and the public domain, have overcome problems, found solutions, learned more about the science, and made progress step by step by step.
Scientific break-even is getting as much energy out of the system in terms of fusion neutrons as the energy you put into the hot plasma. That's the first hurdle of many. There is one facility in the country that has achieved scientific break-even. It's the National Ignition Facility, the laser facility in California. It's a tremendous accomplishment. And I would say on Z, we hope to be achieving scientific break-even sometime in the next 5 years.
We'll need energy from somewhere. If we don't get that energy, then the quality of life will suffer.
We want to have an alternative. May not be the best idea in the world to continue to burn fossil fuels at the rate we're burning. So, I mean, one has to do something. One can't just give up.
We as a community have created a lot of the physics and understanding that we need in order to build a power plant. The blank spaces in the map that need to be filled in are a lot smaller than they used to be.
If we look at the strides that have been made in clean energy, such as solar and wind and biofuels in the last 2 decades, it's just been stunning. The United States isn't investing enough in energy technologies writ large, not just fusion. The funding for all forms of energy should go up, especially clean forms.
The research on fusion that we're doing today is leading to a future where we have fusion-powered electric generating plants to meet our need as a high-tech industrialized society.